I hope everyone's doing well. So we'll keep moving with the material and start talking about probability distributions. Uh, so this is the basics into probability distributions, what we call a discrete probability distribution. That's what we'll do in this session. And in the next session, we'll move on and talk about continuous probability distributions and build into inferential statistics, right? So we're going to cover only two sections of this chapter, the first two, 4.1 and 4.2. So we'll talk about what probability distributions are in general, and then we'll take a look at one very important and specific kind of a probability distribution, what we call the binomial distribution. All right. So let's just dive into the material and start talking about probability distributions. So as a quick roadmap as to what we're going to do, we'll talk about what random variables are, what's the difference between a discrete random variable and a continuous random variable, how do we construct a probability distribution, what does graph look like, and we also talk about what properties a probability distribution should have, right? And as usual, we'll go on and then talk about how to calculate the mean, variance, and standard deviation, the standard summary statistics for a probability distribution. And we'll talk about a key idea around here as to what we call expected value. All right. So that's the big roadmap. As we go along, it's important to keep in mind how these pieces fit into each other. Okay. All right. So let's start with definitions as we always do. Let's talk about a random variable. Okay. So as the name suggests, there's two components to it. It's one of those things in mathematics which is properly defined, where the name itself tells you what is going on. First of all, we are talking about a variable, right? A variable is anything which can take different values, right? It doesn't take a fixed value. It can take multiple different values. That's what makes something a variable. Random essentially means that it can take each of these values that we are talking about with different probabilities, right? So there are multiple different outcomes, and there's probabilities with which each of these outcomes will show up, right? So this is usually denoted by a lowercase x. When we see a lowercase x, it's generally referring to a random variable. And again, remember, random variable by definition is a variable, which means that it can take multiple different values. So it's not a fixed value. X can take multiple different values and take each of these different values with different probabilities, right? That's what makes it random, right? So we don't know ahead of time what value this variable can take. All right. So for instance, let's look at a couple of examples. The number of sales calls a person makes in one day, right? So if you think about this, there can be any number of different values X can take here, right? And the number of sales calls, it could be zero, the person makes no calls, one call, two calls, 100 calls, whatever it is. There's any number of different values this variable X can take, and it'll take each of these values with different probabilities. We'll talk about where those probabilities come from in just a second, but for now it's important to keep that in mind. Okay. The second example, hours spent on sales calls per day. Again, similar story. It could be 0 hours, it could be a minute, it could be a second, it could be 30 minutes, an hour. There is a whole range of different values X can take, and we don't know ahead of time what value X will take. So it's a variable, but it will take each of those values with a different probability. So that's what makes it random. Okay. So we'll first spend a lot of time talking about the difference between a discrete random variable and a continuous random variable. It's important to keep this distinction in mind. With a discrete random variable, the number of outcomes, the number of values X can take is finite, right? Or in layman's terms, it's countable, right? We can look at all the set of outcomes X can take, and we can actually count them all up. We can tell these are the number of values that X can take, right? So if you can think about the number of sales calls a salesperson makes, they could make zero, they could make one, they could make two, they could make three, so on and so forth. But we can count how many different outcomes there are for X, right? The number of outcomes for X is finite or countable. That's what makes it a discrete random variable, is that the number of outcomes is defined and countable, right? You can actually put a number on the number of different outcomes X can actually take. The other version of random variables is a continuous random variable, right? A continuous random variable is a random variable where the number of outcomes is uncountable, right? There's an infinite number of values that X can take. So for instance, if you consider the hours spent on sales calls in one day, right? So there's limits on it. So if the lower limit is 0, you can spend 0 hours making sales calls, or you can spend the entire day, which is limited by 24 hours. But anything in between 0 and 24 on this number line is a possible value, right? It's not just um, 0 hours or 1 hour. Anything between 0 and 1 hours is also a possible value. So it could be a minute, a second, a tenth of a second, a millisecond. You can break this, in mathematical terms between any 2 points on a number line. There's an infinite number of points, right? You can break it into smaller and smaller pieces, and we can't count them because it's infinite, right? There's an infinite number of points which exist between 0 and 24. So the number of outcomes for X is not countable, right? That's what makes it a continuous random variable, that the number of outcomes itself is not countable, right? So again, let's take a couple of examples to just make sure we can fix ideas here. So think about this situation: the number of Fortune 500 companies that lost money in the previous year, right? So Fortune 500, so it's limited by 500 companies, but it's either 0 companies lose money, or 1, or 2, or 3, or at the other end 500, right? So there's 501 different possible values X can take. Why 501? So it can take any number from 1, 2, 3, all the way to 500. That's 500 plus the 0. So the number of outcomes that X can take is countable, right? In this case, it can take 501 different values, and we know that that's it, right? We can count the total number of outcomes that X can take. So this makes it a discrete random variable, right? The number of companies themselves can be counted. All right. Here's a second example to fix ideas. The volume of gas in a 21-gallon tank, right? So you have a 21-gallon tank, and there is a volume of gas here. So you could have no gas, you could have a full tank, but anything in between is possible, right? You could have a gallon of gas, a half gallon, a quarter of a gallon, a little bit, a lot. There is a lot of different values X can take, and we can't count them because it's continuous in a certain sense. Every single drop of gas which goes into the tank is a possible value for X, right? So this is a classic case where the number of outcomes, the number of values X can take, is not countable because there's an infinite number of values that X can take. So that's what makes this a continuous random variable, right? So the amount of gas in the tank can be any volume between 0 and 21 gallons. So you can think that 0 is a possible value, 0.0000001 is a possible value, 0.02 is a possible value. There's an infinite number of values X can take, and that's what makes it a continuous random variable, okay? So it's important to keep this distinction in mind as to whether we are dealing with a discrete random variable or a continuous random variable. It'll become more important as we go along, but it's one distinction that we need to draw, okay? So let's look at a probability distribution. So again, with a random variable, it has two components, right? It has the values itself that X can take. The second component is the probabilities with which X will take any of these values, right? Okay, so for a probability, we know that one condition is that the probability that X will take a particular value is always between 0 and 1, right? It's a fraction, it's always going to be 0 and 1, and the sum of all of these probabilities is always going to add to 1. This is just basically, by definition, when we talk about probabilities, this is how probabilities are defined, is that any particular outcome will have a probability between 0 and 1. The sum of the probabilities for all outcomes is basically 1. Okay? So when we construct a discrete probability distribution, again we start with the basic idea of a frequency distribution, right? So we start with a frequency distribution. We know how to essentially make a frequency distribution table. Then we find the sum of the frequencies, and then we find the relative frequency for each possible outcome, and check to make sure that each of this probability is between 0 and 1, and the sum is 1. Okay, that's the recipe. That's how you construct a probability distribution for a discrete random variable, right? So again, to fix ideas, I think it's useful to look at an example first, and then I think everything else falls into place from there. Okay. So here's a situation we are faced with. So an industrial psychologist is administering a personality test, right? So they're trying to figure out about passive aggressive traits for 150 employees, right? So individuals were given a score from 1 to 5, where 1 was extremely passive, 5 was extremely aggressive, and a score of 3 indicates neither trait, right? They're neither passive nor aggressive, they're in the middle. All right, so think about the score, right? A score for an individual, right? So the first thing to recognize is that it's a discrete random variable. Why? Because if you think about the values x can take, I can give them a score of 1, a score of 2, a score of 3, a score of 4, a score of 5, right? These are only the 5 different values x can take, and I can count them, that there's only 5 different values, and that's what makes it a discrete random variable. Okay. So the first thing is to recognize that the x can take a finite number of values, and we can actually count up the finite list of values and actually list them all out. Okay. Now for each of these scores, for the 150 people we talked to, these are the scores that came out. So 24 people got a score of 1, 33 people got a score of 2, 42 people got a score of 3, 30 people got a score of 4, and 21 people got a score of 5. Okay, so we already have a frequency distribution in mind. X is a discrete random variable because it can take multiple different values with different frequencies, right? That's what it means for it to be a random variable, because it can take different values and it'll take them with different frequencies. All right. So given that this is a basic setup, we can go on and construct a probability distribution. Okay. So if I think about the probability that x will take a value of 1, the probability that an individual will get a score of 1 is just the relative frequency, right? So out of the 150 people inside my sample, 24 of them score 1, right? So the probability that x is equal to 1 is basically 24 over 150, or 0.16. The probability that x is equal to 2 is 33 over 150. Of the 150 people in my sample, 33 is the number of people who scored 2, right? The probability that x will take a value of 3 is 42 people out of 150, so that's 0.28, and so on for the other two, right? So we can essentially construct a probability distribution by listing first the different values x can take, 1, 2, 3, 4, or 5, and next, in the next row, listing the probabilities with which x will take each of these values. So this essentially says that the probability that x will take a value of 1 is 0.16, and that's coming from this calculation of the relative frequency. Okay. So the probability that x will take a value of 2 is 0.22, and that's coming from here, the relative frequency of that category, right? So this representation where we have a list of the values x will take and the probabilities with which x will take each of these values, this is what is referred to as a probability distribution, right? To make sure that this is a valid probability distribution, we need to check for two conditions. We need to check that any of these values here, the probabilities which are attached to any of these numbers, are between 0 and 1. Right? That's the first thing, is to check that the probabilities are always bounded on the lower end by 0 and on the upper end by 1. So if I look at each of these numbers, that satisfies the conditions, right? Each of these numbers is a fraction between 0 and 1. The 0.16 is between 0 and 1. 0.22 is a value between 0 and 1. And the other three values are also between 0 and 1. So it meets the first criteria that the probability is always between 0 and 1. The second criteria for a valid probability distribution is to make sure that if I sum all these probabilities together, that they sum to 1, right? So if I sum all the probabilities together, so 0.16 plus 0.22 plus 0.28 plus 0.20 plus 0.14, that sums to 1. Okay. One quick thing is to note here is that because we calculate these fractions, right? Because we calculate these as fractions, generally we might not get, like, we have to round these numbers up, right? So it might not always sum precisely to 1. It's somewhere close to 1, right? It might be 0.999 something or 1.000 something. That's fine, right? That's fine because that's basically due to the rounding error. So if you didn't round, you would get precisely 1. But if you did some kind of rounding, then it would be slightly different than 1. That's okay, right? But it meets the two criteria for a valid probability distribution, that each of these probabilities is some number between 0 and 1, and then the sum of the probabilities of all the probabilities is also equal to 1. Okay, so I can go ahead and actually put this down on a graph, right? So I can actually visually look at this situation here. So on the y-axis, I'm measuring the probability of x. On the x-axis, I'm measuring the different values of x. So the way it's graphed is that x will take a value of 1 with this probability. The height of this rectangle represents the probability, so that's 0.16. And so this rectangle basically tells me the probability with which x will take this value. So the height of this rectangle tells me that the probability with which x will take a value of 2 is 0.22, and this on. Right? It's basically a relative frequency histogram, but with the labels changed a bit. Right? With the relative frequency, here we would have seen relative frequency, but we are just reinterpreting the relative frequency as a probability. So we write this as the probability of x, and now we have a nice little graph for the probability distribution. Right? All right. Okay, so again, if there's any questions on anything we've talked about so far, the comments thread again under the video is open. So if you have a question, anything which comes up, then please ask your question there, and I'll try to answer it as promptly as I can. And if again, we have office hours on Friday, and you can ask me questions there as well, but just make sure that if there's anything which comes up, given the format in which the course is being conducted, just make sure you ask your question down there, and I'll try to respond. So if other students have a good response and they think they know the answer, you can jump in and respond as well. And if there's any errors, I can correct as well. All right. Okay. Then the usual suspects, we want to calculate the mean, the standard deviation, and the variance of probability distributions. So first, let's talk about the mean, right? Let's talk about summary statistics. So the mean for a discrete probability distribution is that you take each value, multiply it by its probability, and then add up all of these things. So this basically says it's the sum of x times p of x, right? So we'll take a look at the example that we have to show how this works. So if I have to find the mean here, right, what I would do is that I take each value and multiply it by its probability. So 1 times 0.16, x times p of x, 2 times 0.22, 3 times 0.28, so on and so forth. And then I would add up all these products, right? So this is, I take each value, multiplied by its probability. So x times p of x 0.16 plus 2 times 0.22, which is 0.44, plus 3 times 0.28, which is 0.72, plus 4 times 0.20, which is 0.8, and 5 times 0.14, which is, I want to say 0.8 as well, right? So if I add up those 5 numbers, if I add up those 5 products, that tells me the mean of the discrete probability distribution. I get 2.94 or 2.9, right? Okay, so that's how I find the mean for a probability distribution, right? I take each value, multiply it by its probability, and then I add up all the products. That's what the notation here says. Take each value, multiply it by its probability, and add up all those products together, and that tells me the mean of this probability distribution. Okay. So the other two summary statistics that we want to find are the usual suspects, variance and standard deviation. There's one little error in my notes here. So with variance, there's no square root. So I put it there. So I'll try to correct the notes before I post them. But here shouldn't be a square root. This is not right. So it's just basically you take each value, subtract the mean from it, square it, the usual suspects. But now you multiply that by its probability and then add them all up, right? And for the standard deviation, you just take the square root of the variance, so this is fine. So you take each value, subtract the mean from it, square that deviation, multiply that by the probability, and then add those products up together and then drop the square. Okay. So in our example, we have this probability distribution. So x, these are the different values for x, these are the probabilities with which x will take that value, and we already calculated the mean, right? Remember that we already calculated the mean, which was 2.94, right? Okay, so again, remember the mean was already calculated, so the first um, business is to first find deviation. So take each value, so x takes a value of 1, the mean is 2.94, so the deviation here is negative 1.94. Take the value 2, subtract the mean from it, and I get a deviation of negative 0.94. Take the value 3, subtract the mean from it, I get a deviation, a fourth, and the fifth, right? So to find the variance, I take each of these numbers. So I would square this number, right? So what I would do here next is to take this number negative 1.94, right? I would square this number and then multiply it by 0.16, right? So I would multiply that by 0.16. Alright, so I would take each of these deviations, square them, and multiply that by the probability, which is 0.16. Then I would do the same thing for this value. So I take negative 0.94, square it, multiply that by 0.22, and then I would take this value, square it, multiply it by 0.28, then this value, square it, multiply it by 0.20, and then once I have that column, I would add that entire column up. That's what the sum here is, and that tells me the variance of this particular probability distribution. Okay, so if I take the square root of the variance, I get the standard deviation. All of this is basically this usual story that we have. Okay, I hope that's clear. Again, if there's any questions, feel free to comment below or ask me during office hours. Okay. The last thing in this section that I want to talk about is this notion of expected value. Right? Expected value is just a way of talking about the mean of a probability distribution. So when we say expected value, what we mean is that on average, what is the value of x, right? So on average, what do we expect the value of x to be? That's what we call this expected value. It's just a way of talking about the mean itself. Again, so the mean is given as x times p of x. So take each value of x, multiply it by its probability, and then add the column up of those products, and that tells me the mean. Okay. So let's take an example to see how we find expected values here, right? So you go to a raffle, right? So there's a raffle. So you buy 1,500 tickets are available for purchase. To buy or enter this raffle, it costs $2, right? You spend $2 each to get one of these tickets, and there's four prizes. Four of these tickets will win you prizes, right? One ticket will win you $500. One of them has a price list of $250. Another one will get you $150, and the fourth one will get you $75, right? So if you buy one ticket, what is the expected value of your game, right? What do you expect on average to happen? Okay. So think about all the outcomes that can happen. Okay. So if I think about all the things that can happen, I could end up in one of five situations, right? One of five situations. I buy a ticket, the ticket gets me a $500 prize, right? So I'll get a $500 prize for having the prize winning ticket. I paid $2 to buy the ticket, so I make in net $498 if I win the $500 prize. I could win the $250 prize, in which case I'd make $248 in net because I'll win. The price is $250. I paid $2 for the ticket. In net, my profit is $248. I could win the $150 price ticket, in which case I would make $148, or I could win the $75 price ticket, and then I would make a profit of $73. And I could end up with not winning a ticket at all, in which case I'd just lose the $2 that I spent buying a ticket, right? So if I enter into this raffle, I know that there are 5 things that could happen. I could end up winning $500, 250, 150, 75, or nothing, right? So it's a random variable in the sense that um, one of these 5 outcomes is possible. It's a discrete random variable in the sense that I can count up the number of different things that can happen. In this case, there's only 5 things that can happen. Okay. Now, the question is, what do I expect to make on average, right? If I just went in blindly, bought a ticket, what do I expect to happen on average? So I want to know what the mean of this probability distribution is. So I know what the outcomes are. I know what the different values for X are. The next thing is to find the probabilities for different values for each of these values, right? So if I think about X as a random variable which can take one of 5 values, I can make 498 profit, 248 profit, $148 profit, $73 in profit, or I could lose $2. So the probability that I make a $498 profit is the probability that I end up with the ticket which wins me the $500 prize. There's one of those out of the 1500 that are sold. So the probability that I make a profit of $498 here is 1 over 1500, right? There's only one ticket which will get me $500 profit. I subtract the $2 that I paid for the ticket, which is my gain is $498. So the probability that I end up with this ticket is 1 over 1500. Similarly, for the ticket with $250 printed on it, I pay $2, so my gain is 248. And the probability that I have this ticket is that there's 1500 tickets which were sold, only one of them will make this gain. So again, similarly for this and this, right? So 1 over 1500 is the probabilities for each of these 4 outcomes. And the probability that I lose money, lose my $2, is that of the 1500 outcomes, 1496 don't have any prize money attached to them. So the probability that I lose $2 from this transaction is 1500 tickets were sold, 1496 of them will cost me $2 but will not return some gain. Okay, so if I calculate the expected value of X, so I would make $498 with a probability of 1 over 1500, plus I would make $248 with a probability of 1 over 1500. So this is X times P of X, X times P of X. So for each of these values, I take the value of X multiplied by its probability, and then plus take this value multiplied by its probability, plus the third value multiplied by its probability, the fourth value and multiplied by its probability, and then the fifth value and multiplied by its probability. And it turns out, if I run the math on this, that the expected value of this raffle is $1.35, negative $1.35. So on average, right, if I go in and buy a ticket, on average, I expect to lose $1.35, right? So one way to think about this number is that if I buy a lot of these raffle tickets, right, most of those tickets I'm going to lose money on, right? But if even one of those tickets ends up being a prize winning ticket, I might be able to offset those losses. That's why the expected value of the lottery is not negative $2. You don't lose $2 for sure every single time, but if you buy a large enough number of tickets, you will lose $2 on a lot of them. But if one of the tickets that you ended up buying is a prize winning ticket, you might be able to offset the losses that of buying all of these tickets. Okay. A second way to interpret this exact same situation is to say, if I bought all 1500 tickets, okay, if I bought all 1500 tickets, what do I expect to make, right? So if I bought all 1500 tickets, I would have the 4 prize winning tickets, but it also cost me a lot of money to buy all 1500 tickets. On a net basis, I would end up losing $1.35 on average, right? So the expected value tells us, in a certain sense, it's very crucial to get your mind around this concept of an expected value. It tells us, given that there is uncertainty around outcomes for a particular situation, what can I expect the average outcome to be, right? That's what it means for it to be an expected value, that on average, this is the outcome I think will happen, right? Okay, so that basically covers section 4.1. So It's a quick introduction into probability distributions, into distinguishing between discrete and continuous probability distributions, and then how to calculate the mean, the variance, and the standard deviation for a probability distribution, and this notion of an expected value. Right? So, fairly straightforward. It's basically rejigging what we already know about the relative frequency, and we're just calling the relative frequency the probability. Right? That's basically the big difference in this case. Okay. I hope that's clear. I hope this mode is working. Um, all right, so we'll go on and talk about a very special kind of a discrete probability distribution, one of the most important probability distributions in general that we talk about, this notion of what we call a binomial distribution. All right, so with a binomial distribution, the first thing is to ask, what is a binomial experiment, right? What is a binomial experiment? So there's a specific criteria for this situation or experiment that we're doing to meet for it to be called a binomial experiment, right? Then we'll talk about the binomial probability formula and different ways of calculating these numbers. And we'll talk about the distribution of a binomial, how to graph this distribution. And then again, the usual suspects, we'll talk about how do I find the mean, the variance, and the standard deviation for a binomial distribution. Okay. All right. So let's talk about a binomial experiment. Okay. A binomial experiment is basically, this is also what we call a Bernoulli trial, right? A Bernoulli trial is that each trial is independent of other trials, right? The first thing is that I conduct this experiment many times. I conduct multiple trials, right? So my experiment, if I think about the overarching framework, my entire experiment consists of doing one action a repeated number of times. So I conduct the same trial multiple different times for a fixed number of times, but each of what happens on any of these trials is independent of what happened before or what comes after, right? There is no dependence between the different trials, right? Each trial is as if it's its own independent thing, and what happened before has no effect on what happens next. Okay. The second thing for it to be a binomial experiment is that on any given of these trials, there's only two outcomes, right? I can either classify them as a success or a failure. That there's only two outcomes. That's what makes it a binomial, right? Bi meaning two, that there is only two outcomes for each of these trials. One I'll call success, one I'll call failure. So it's up to me as to classify what I see as a success and what I see as a failure. But the crucial thing to recognize is that there is only two possible outcomes on any given trial. Okay. So the probability of success, the probability with which I get a success on any given trial, is the same for each trial. This is again goes back to the fact that the trials are independent. So the probability of success on any trial is the same across all the different trials. Okay. The fourth thing to recognize here is that there is a random variable x, right? So there's a random variable x which counts up the number of successful trials. So x is basically a way of keeping track of how many of these trials that I've conducted are successful. Right? So that's the big definition around the binomial experiment. So if I look at it, I can basically describe a binomial experiment using four different key numbers. Right? The first thing inside a binomial experiment is how many times do I do this trial, right? N here represents the number of trials, number of times a trial is repeated. How many times have I conducted this trial over and over? P here tells me the probability of success on any given trial. We'll talk about how to find this in just a moment, but P here essentially captures what is the probability that any of these trials is successful. Q is basically 1 minus P. So it basically records the probability of failure. So if this is the probability of success, then 100% of the time it's either a success or a failure. So if P is the probability of success, so if 85% of trials are classified as successful, 1 minus 85%, 0.85, or 15% of the time the trial is classified as unsuccessful. X here is a random variable. X is basically going to keep track of the number of trials as we go along, right? As the number of successful trials as we go along. And X, if you can think about it, is a counting variable, right? It's just going to count up how many of the trials that I've conducted are successful so far, right? That's basically the setup we have in mind. Okay, so let's look at a couple of examples to determine whether the situation we're dealing with is binomial or not, right? Because the crucial element is to recognize whether you're dealing with a situation which can be a binomial experiment or not. Because if you can determine that it's a binomial experiment, then there's a set of formulas that we can use to basically find probabilities. Okay. Okay. So let's think about this situation. A certain surgical procedure has an 85% chance of success, right? So a doctor performs a procedure on 8 patients. The random variable represents the number of successful surgeries. Okay. So think about what the situation is saying, right? Each surgery is a trial, right? So I conduct 8 surgeries, which is a way of saying that I have 8 trials. So this is 8 different times I conduct the same surgery, and so there are 8 different trials, right? So, and each one is independent of the other ones. So what happens on a particular surgery has no bearing on what happens on another surgery. They're all independent of each other, so the trials are independent of each other. Okay. The second thing is that there's only 2 possible outcomes for any of these surgeries. For on each trial, there is only 2 possible outcomes. Either it's a success, either a classified as a successful surgery, or it's a failure, right? Where the surgery doesn't work and it's a failure. So there's only 2 possible things that could happen on any given trial. The probability of success for a trial is 0.85. Tells me that 85% of surgeries are successful, which tells me that the probability of success on any given trial is 0.85 for each surgery. Right? And the random variable x here is going to just keep a track of the number of successful surgeries. Right? So if I express this in my numbers, in my 4 key numbers, n here is 8, right? So the number of trials here is 8. P here is the probability of success on any given trial, 0.85. Q here is the probability of failure on any given trial, 0.15, 15%. And X is a random variable which keeps track of the number of successful surgeries. So X can take a value from 0, which means that none of the surgeries are successful, 1, 2, 3, 4, all the way up to 8. And it's a discrete random variable, right? Because X can take only one of 9 different values. So this is a case where I have a binomial experiment because it meets all the criteria where I conduct the same action multiple times. The probability of success and the probability of failure are the same across all of these trials, which means that the trials are independent of each other. And I have a random variable which is keeping track of the number of successful surgeries as I go along, right? As I keep going along, it keeps a track of the number of successful surgeries. Okay? All right. Let's consider a different situation. Okay. So we consider a situation where a jar contains 5 red marbles, 9 blue, and 6 green. Right. So the jar consists of, if I count them up, 9 plus 5 is 14 plus 6 is 20. So there's 20 marbles which are inside this jar, 5 of which are red, 9 of which are blue, and 6 of which are green. Right. So you randomly select 3 marbles from the jar without replacement. So you're going to take these marbles one after the other out of the jar, but you're not going to replace them once they come out of the jar. Okay. The random variable represents the number of red marbles. Okay. Okay. X here will keep track of the number of red marbles. Okay. So one thing is that I could classify this as a binomial in a certain sense where I say a trial is successful. A trial is when I stick my hand inside the jar and pull out a marble, right? So I'll do this 3 times. So I conduct 3 trials. I'll say a trial is successful if when I stick my hand into the jar, if I pull it out, it's a red marble. If I get a red marble, I say it's a success. If I get any of the other 2 colors, if I get a blue or a green, I could say it's a failure. Right? So I can describe this as a binomial experiment because if I see a red marble, I call it a success. If I see anything else, I call it a failure. Right? All right. So let's think about the probability of getting a red marble on the first try. Right? So I stick my hand into the jar. There's 20 marbles to choose from. right? And 5 of which are red. So the probability that I get a red marble on the first trial is 5 over 20. Okay. So I pick up the first marble, put it away. Okay. So I go in, right? I go in, and if I go in for the second trial, when I go in to pick a marble the second time, there is only 19 marbles left. Okay. So because I already took one marble out and I didn't replace it back in the jar, when I go in for the second trial, there's only 19 marbles left. So if the first marble that I picked out was 4 over was a red marble, then the probability of getting a red marble on the second trial is now 4 over 19, right? Because I pulled one marble out and didn't replace it, which means that there's 19 marbles left in the jar at the start of the second trial. And the first marble that I pulled out was a red marble, which means that instead of 5, there's only 4 red marbles left inside the jar. So that could be 4 over 19. Another case is that, okay, so I have 19 marbles left, and suppose the first marble that I pulled out was not a red marble, but was of a different color, then I would have 5 red marbles left. Right? I could have one of these two situations. But the crucial thing is to recognize that these two, whether I'm here or here, is different than the probability of getting a red marble was on the first trial. Right? So the probability of getting a red marble is changing as I go along, right? Because as I go along, as I do multiple trials, I'm removing marbles out of the uh, jar and not replacing them. So the probability is getting altered. The probability of getting a red marble is getting altered as I conduct more and more trials. So this is a case where the trials are not independent because I'm not replacing the marbles back into the jar once I pull them out. The probability is changing with each trial. The probability of success itself, the probability of seeing a red marble is changing with each trial, which tells me that this is a case where it's not a binomial experiment. Right? It's not a binomial experiment because the probability is not constant across the different trials. Okay, so the crucial thing to ask yourself when you're faced with a situation where you can classify outcome on any given trial as success or failure is to ask, is the probability of success changing between trials or is it staying constant? If it's changing, we have a problem. It's not binomial. If it's staying constant, then that's fine. Then we can move ahead and check for the other conditions for a binomial situation. Okay. All right. Hope that's clear. So we'll keep going and talk about the binomial probability formula. Okay. We have a nice clean formula for finding probabilities, right, inside this setup. So here, again, to read through the notation, the probability of X is the number of successful trials out of the n total trials that I conducted. The probability that X successful trials out of n possible trials is given as NCX. This is the combination. Again, remember NCX from the previous lecture. This is a combination. So n trials are conducted, X of them are successful, and it's a combination. We don't really care the order in which the trials are successful, times P raised to X. P is the probability of success on any given trial raised to the number of successful trials, times Q, the probability of failure, times the number of unsuccessful trials. Right? NCX, remember the formula comes down to n factorial over n minus x factorial times x factorial. Right? That's basically the formula for NCX. So that's times p raised to x times q raised to n minus x. Okay. So that's the binomial formula. So we'll go with binomial probability formula. So let's take a couple of examples to see how to apply this uh, in real situations. Right? Okay. So we're faced with the situation where microfracture knee surgery has a 75% chance of success. Right? So the probability of success is given to be 75%. Okay, so we know what P here is. P here is 0.75. If you know P, you know Q, right? Q is 0.25. The surgery is performed on 3 patients, right? 3 trials are conducted, so N is 3, right? Find the probability of the surgery being successful on exactly 2 patients. right? The number of successful trials is 2. X here is basically 2. Okay. All right. So the first method, well, we'll come back to it. This is not particularly a useful method in this case. So we'll look at using the binomial probability formula. N is the number of trials, right? I'm going to conduct this surgery 3 times, right? 3 times. N is the number of trials. The probability of success on any trial is 75% or 3 over 4. Okay. The probability of failure on any one of those terms is 25% or 1 over 4. The number of successful surgeries that I want to consider is 2. X is exactly equal to 2. So the probability of having exactly 2 successful surgeries, right, X is equal to 2, is NC2, right, 3C2. NCX is 3C2 times P raised to X. P here is 3 over 4. X here is 2 times Q, which is a probability of failure, which is 1 over 4 raised to n minus x, the probability of the number of failures, right? So n minus x is 3 minus 2, which is 1. Okay. So 3C2, again, the formula, remember, is 3 factorial over 3 minus 2 factorial times 2 factorial. That's the formula for the combination, times p raised to x times q raised to n minus x. And if you simplify that, it turns out that the probability that exactly 2 of these surgeries are successful is 27 over 64. Okay. So if I go back, I can look at it in the tree diagram as well, right? This is not particularly useful in more complicated situations, but this is just to make sure that you understand that it's basically intuitive as to what's happening. So consider this, my experiment consists of 3 parts, 3 surgeries, 3 trials are conducted one after the other. On the first surgery, I can have a success or a failure. Given that the first surgery is a success, I could have a success or a failure on the second one. Given that the first and second are successful, I could have a success or a failure on the third one, right? Similar situation, so I have built out this tree diagram. We've seen and dealt with how to do this many times. So if I think about this outcomes for these 3 surgeries conducted one after the other, I could be in one of these situations. SSS, which essentially says success, success, success. So the first one is successful, second one is successful, third one is successful. SSF means that SSF, I end up in this sequence of outcomes where the first 2 are successful, the third is a failure. Okay. And so on. So I can count up the total number of outcomes where the total different outcomes are there. Okay. In each of these cases, I know the number of successes. So in the first one, I have all 3 successful. The second one, I have 2. The third one, I have 2. SFS means that the first is successful, second fails, third is success. So 2 successful. SFF means first success, second failure, third failure. So there's only 1 success, so on. Okay. So if I want to know the probability that exactly 2 of these surgeries are successful, I want to know what is the probability that I'm here, or the probability I'm here, or the probability that I'm in this situation. Right? The probability that I end up in this situation is the probability that the first one is successful, which is 3 over 4, times the probability that the second one is successful, which is times 3 over 4, times the probability that the third one is a failure, which is times 1 over 4, or 9 over 64. Okay. The probability that I end up in this situation is the probability that the first one is successful and the second one is a failure, which is 1 over 4, and the third one is a failure. This is just using the multiplication rule. Right? That's 9 over 64, and the probability that I end up here is that the first one is a failure is 1 over 4 times the probability the second one is a success is times 3 over 4 times the third one is a success is times 3 over 4, or 9 over 64. So I could end up in one of these 3 things. So if I add up these 3 probabilities, that's 27 over 64. 3 times 9 over 64 is 27 over 64, and that's what we have here. Okay. So the binomial formula is basically trying to simplify or basically in a notational sense, simplify how we calculate these probabilities. Okay. All right. So we can come up with numbers for each of these, right? So if I had to fill out this probability distribution table for this situation, I know n is 3, I know p is 3 over 4, which means q is 1 over 4, and I can find the probabilities using the binomial probability formula to find each of these values. Okay. So we'll take a second example where we'll do exactly that. We'll build the binomial probability distribution out from scratch. Okay. Right. So we took a survey, US adults, right? We are surveying US adults, and we asked them give reasons why they like texting on their cell phones. Okay. So here's the information that we have. They said convenient for basic information, works where talking won't do, quicker than calling. But this is basically the distribution of the responses. 7 adults. So we are going to talk to 7 people. So you can you can imagine that each of these situations is a trial. So there's 7 people I'm going to talk to, one after the other. Each of them is independent of the other. So there are 7 random people. So each of these situations is independent of the other. Okay. We ask them, do you like texting because it's quicker than calling? So if they say yes, that's the reason I like texting better, we would say that's a success. We would define that as success. If they give me any other reason, I would say it's a failure, right? So the probability here for a successful response on my question is 56% or 0.56. Okay. So if I had to construct a binomial probability distribution, this is how I would go about it, right? First, 56% of adults like texting because it's quicker than calling. So if I had to write down what's going to happen, I'm going to talk to 7 adults. So I'm going to conduct 7 trials. The probability that any of these trials is successful, where I get this particular response, which I'm calling a success, is 56% of 0.56. So if this is 0.56, excuse me. If the probability of success is 0.56, then the probability of failure is 1 minus 0.56 or 0.44, right? X here is a random variable which keeps track of the number of successful um, trials, right? The number of people who say that they like texting because it's quicker than calling, right? So X can take values from 0, where none of them say they like texting better because it's quicker than calling, or 7, where all of them and any number in between. It's a discrete random variable because there's only 8 possible values that X can take. It can take one of these 8 possible values. Okay. All right. So given this the situation, okay. Sorry. Okay. Let me. Get rid of that. Okay. So given that this is the situation, I can calculate the probabilities that X will take any of these values. So the probability that when I talk to 7 people, where the probability of successful response is 0.56, the probability that exactly 0 of these 7 people will say yes is given by the probability that X is equal to 0, and I apply the binomial formula. The binomial formula says that it's ncx times p raised to x times q raised to n minus x, and I've already written everything out here. So here x is 0, so n is 7, so 7c is 0, ncx 7c0 times p, which is 0.56 raised to x, x here is 0, times q raised to n minus x. N is 7, x is 0, so 7 minus 0 is 7, so I can calculate this number, right? How do I do 7c0? It's 7 factorial over 7 minus 0 factorial times 0 factorial. Remember, 0 factorial is 1, so I get 1. Okay. So again, the probability that x equal to 1 is 7c1, right? X is now 1, so 7c1 times p raised to x, which is 1, times q raised to n minus x, which is 6, right? So again, probability that x equal to 2, x equal to 3, x equal to 4, 5, 6, 7, right? So I know the different values of x, and I know the probabilities with which x will take each of these values, right? So I know what the different values x will take. I know the probabilities with which x will take any of these values, which means that I can go ahead and construct a probability distribution chart, which essentially lists all the different values x will take and the probabilities with which x will take any of these values, and that's basically what I have, right? I can make sure that this is a valid probability distribution by checking to make sure that each of these numbers is between 0 and 1, which they are, and then checking to make sure that if I add all of these probabilities together, that they sum to 1, right? In this case, they sum to 1.00001 because there's some rounding errors in how we've rounded these numbers up, but it's basically close to 1, okay? All right. Again, the homework has enough questions on this to make sure that these ideas are fixed in place. So if there's any questions, again, the comments below, or see me in office hours on Friday. Okay. All right. So let's take a second example and see how to apply these ideas. So we took a survey. The survey indicates that 41% of women, so here we have a crucial thing, 41% of women consider reading as their favorite leisure time activity, right? So P here is 0.41. The probability that they say that reading is their favorite leisure activity is 0.41, 41%. You randomly select 4 US women, so you're going to ask 4 of them, so the number of trials in the situation, N is 4. If reading is their favorite leisure activity, so you're going to talk to 4 of these 4 women at random, and you're going to ask them, is reading your favorite leisure activity? If they say yes, we say it's success. If they say no, we say it's a failure, right? Find the probability that at least 2 of them respond yes. Okay, so consider the situation we are. Okay, so N is 4. We are going to talk to 4 of them, so we're going to conduct 4 trials. The probability that one of those trials will give an answer of yes or a success is 0.41. That's coming from here, which means that immediately the probability of failure is 1 minus the probability of success, 1 minus p, or 0.59, right? The second thing, so I hope this part is clear. This part should be ironclad by now. So N is how many trials I'm conducting. P is the probability of success, getting a successful response on one of those trials. Q is the probability of receiving a failed response on one of those trials. And at least 2 here means that 2 or more, right? 2 or more. So we need to find the sum of the probabilities of P2, P3, P4. Right? 2 or more is 2, 3, or 4. Okay. So I apply the binomial probability formula. So probability that P2, right, the probability that x is precisely 2 is NCX 4C2, because n is 4, x is 2, so 4C2 times p raised to x. P here is 0.41, raised to x here is 2, times q, which is 0.59, raised to n minus x, 4 minus 2, which is 2. Okay, so I can calculate the probability of 2, probability that excuse me, probability that x will take a value of 3, and then probability that the x will take a value of 4, and then the probability that x will take a value greater than or equal to 2 is the probability that x will be 2, plus the probability that x will be 3, plus the probability that x will be 4. So I sum these 3 numbers together, and that tells me the probability of x being greater than or equal to 2. Okay, which is 0.542. Right? So this is again, we are just applying the binomial probability formula to get to these numbers, to get these numbers up. Right? And then we are applying the addition rule here to find the probability for the given situation. Right. This a second way of finding binomial probabilities using a table. We're not going to use this for this class. I'm going to skip over these two slides. I've left them in there because if you're interested, you can take a look and see how to use the table itself. But maybe you can just skip over these two slides. Okay. All right. The last couple of things that I want to talk about is to basically you can graph a binomial distribution, right? So consider a situation where 60% of households in the US own a video console. So 60% is the probability of success, right? If I pick up a random US household and I ask, do you own a video game console? The probability that they say, yes, we do have one is about 60%, 0.60, right? That's where P is coming from. So which means that the probability of a failure is 0.40, right? I talked to 6 households, right? Select 6 households, so n is 6. So we can find a probability for each of these values of x, right? How do I find these? Again, I say for set x equal to 0, then I do nc0 times p raised to x q raised to n minus x, then x equal to 1. So I can essentially find these different values, right? This entire row is constructed by using the binomial formula that we've been using already, okay? And then we can just put that on a graph, right? So x can take values from 0 through 6, so 0, 1, 2, 3, 4, 5, 6. So x will take a value of 0 with a probability of 0.004, that's what's represented here. Then x will take a value of 1 with a probability of 0.037, that's what's represented here, and so on. All right. Okay, the last thing we need to deal with inside this binomial distribution situation is the usual things about calculating the mean, the variance, and the standard deviation of a binomial distribution, and it's straightforward, right? So there's 3 formulas here. That's what tells us what the mean, variance, and standard deviation are for a binomial distribution. So the mean of a binomial distribution is just given by n times p, the variance is given by n times p times q, and the standard deviation is just the square root of the variance, okay? So let's calculate these for an example. So we have some data about weather. So in Pittsburgh, Pennsylvania, about 56% of the days in a year are cloudy, right? So probability of a cloudy day. So I look at a particular day and I basically define two outcomes. Either the day is cloudy or it's not cloudy. That's what makes it a binomial situation because there's only 2 possible outcomes for it, right? So the probability that a day is cloudy is 56%. So I know P here straight away, that it's 0.56. If I know P and know Q, the probability that it's not cloudy is 0.44. 1 minus 0.56 is 0.44, right? So we want to find the mean, variance, and standard deviation for the number of cloudy days during the month of June. Okay, so let's look at this month of June. If I think about the month of June, it has 30 days. So I'm going to observe the weather on 30 different days. So n here being equal to 30 tells me the number of trials I'm going to observe, right? So the mean here would be for this distribution is just n times p, n is 30, p is 0.56, so 30 times 0.56 is 16.8. So on average in the month of June, 16 and about 17 days roughly speaking are going to be cloudy, okay? The variance is n times p times q, n here is 30, p here is 0.56, q here is 0.44, so n times p times q, that's 7.4, right? Standard deviation here is as square root of the variance, the square root of npq, which is 30 times 0.56 times 0.44, which is 2.7, okay? So interpret the results and determine any unusual values. So what does it mean given that this is the summary statistics we have? The mean tells me on average that there's about 16.8 cloudy days during the month of June, right? That's what this number tells me. On average of the 30 days in June, the average month of June will have about 16.8 precisely, or about 17 cloudy days, right? The standard deviation is about 2.7 days, right? Again, if we observe a month of June which is about more than 2 standard deviation steps away from the mean, we said that was unusual, right? It's a way of just talking about z-scores indirectly, right? So if I have a month of June which is 2 standard deviation steps away from the mean to the left, so 16.8 is the mean, minus 2 is the number of standard deviations. This is the size of each step. So that's 2 standard deviation steps to the left of the mean. So June with 11 cloudy days would be unusual, right? Because it's more than 2 standard deviation steps away from the mean on the left hand side. On the right hand side, plus 2 times standard deviation, about 22.2. So June with more than 22.2 cloudy days would also be considered unusual. So on this end, this is the lower end. So if there's less than 11 cloudy days in the month of June, we'd say, oh, that's unusual for June relative to historical patterns. And if there is more than 23 cloudy days in the month of June, that would also be considered unusual, because on average we're expecting to see about 16.8 cloudy days. Right. So that's it for this lecture. I hope this format is working. So if there's any questions, again, leave them in the comments in the video below. I encourage other students to participate in the discussions below. So if you know the answer to the question, or you think you do, just participate. So if I make sure that there is a steady response from everyone, and that make sure that there's enough participation from everyone here, I'll also jump into the comments thread to answer any questions that you might have. We have office hours scheduled for Friday. I will send out an email later in the week as to how to get in touch with me for that. The next exam is scheduled for April 6th. It will cover chapters 3 and 4, so up until what we have done today. So all of that is going to be on the exam. So, and it'll be online. Again, I'll send out a detailed email as to how the exam will work and when it will be. But that's the material for this week. The 2 videos, one which is finishes up the probability lecture, and the second one which is basically everything around the discrete probability distributions. These 2 videos are what you're supposed to watch for this week. I've posted chapter 4 homework on the PSN platform. I posted the slides on Blackboard, so you have access to all of that as well. I know this is an unusual situation. I hope everyone's taking adequate precautions, staying healthy. Just make sure that you take care of yourselves. And if there's any questions, concerns, I'm here to help. That's it. Thanks for watching, and I'll see you in the next one. Stay healthy, stay safe, and see you soon.